The bicycle has a mass of 13.1 kilograms, and its rider has a mass of 81.7 kilograms. The rider is pumping hard so that a horizontal net force of 9.78 newtons accelerates them both. What is the acceleration? Since it's accelerating, we know that its net force is equal to mass times acceleration. It's not, there is an acceleration here. The force that's given to us is the net force. It's 9.78, so we're going to put that in right here. And of course, the mass is the mass of the entire system. So we need to add together the 81.7 kilograms and the 13.1 kilograms. And that's 94.8. And we're looking for A. Divide by 94.8 on both sides. And that'll give us our acceleration.
0.103. And that's -2. Make numbers. No.
All right. Handle that? Yeah. They get harder. We'll work our way up to it. A person with a black belt in karate has a fist that has a mass of 0.70 kilograms. How do you know what the mass is of just a fist? Trying to figure out how they do that. Starting from rest, the fist attains a velocity of 8 meters per second in 0.15 seconds. What is the magnitude of the average net force applied to the fist achieve this level of performance? So it's moving. It's not a constant velocity, which must mean it's accelerating. So when we're looking for the net force, we know the mass of the fist is 0.70. The problem is I don't know what the acceleration is. So if I write out what I do know, I'm looking for the acceleration. I know it started from rest. I know it attained a velocity of 8 meters per second. And I know it did this in, what, 0.15 seconds? So I don't need that to get it. So I'm needing a formula, one of our kinematic formulas that don't have the S in it. Now, you may or may not remember your kinematic formula, so let me put them on the board. They don't give you the first two, as we learned in our previous section. They don't give you the first two. They don't tell you that the velocity is the displacement over the time. They don't give you the acceleration is the final velocity minus the initial velocity over the change in time. Those two are not given to you in the data booklet. But they do give you v squared equals u squared plus 2as. They give you that one. They do give you s equals ut plus 1/2 at squared. They do give you that one. They do give you s is equal to v plus u over 2 times t. Now if it's accelerating, you're not using the bottom one, and you will never be using the top one if it's accelerating. Because there's no acceleration in it. That makes sense. So we need one of these that doesn't have an s in it. This has an s, that has an s, so this must be it.
Yeah.
So I say A is v minus u over t, bless you, 8 minus 0 over 0.15, and that will give us our acceleration that we can plug in there. Somebody want to calculate that?
Oh, it's 53. Oh, the answer's 37.
This is what?
53.333.
And then we multiply by 0.70 and 37 newtons. So sometimes when they're looking for the net force, you don't have to do all the sum of forces because they're looking for the net force. So we don't always have to do the sum of forces. You actually have to look at what you're given in the problem. Now, I'm pretty sure in number 3 the tennis ball is not 58 kilograms. So we're going to say that it's 58 grams because I'm pretty sure it's not 58 kilograms. So let's see what we have going on here. When a 58-gram tennis ball is served, it accelerates from rest to a speed of 45 meters per second. The impact with the racket gives the ball a constant acceleration over a distance of 44 centimeters. What is the magnitude of the net force? So we're looking for the net force, right? It's a constant acceleration, not a constant velocity. Constant acceleration is different than a constant velocity because gravity is a form of constant acceleration. That doesn't mean we're not accelerating. Okay, so here we are accelerating. Whatever the value is constant. And in fact, that's actually one thing that you have to know about these formulas. The only time you can use those kinematic formulas is under the assumption that it is a constant acceleration. In IB, we don't do anything where our acceleration is actually changing with those particular formulas. So the assumption is that it's constant. Now, what they mean by constant acceleration means it's got constant magnitude, numerical quantity. It has constant direction as well. That's what's meant by constant acceleration. All right, so we have the mass, and that was 58 grams. Now, when you're using this formula, you can't leave it in grams. You have to put it in kilograms. And I need to get the acceleration, so I guess I'm going to have to SUV that. I'm looking for A. What other information they gave me? It accelerates from rest. That would mean your initial is 0. To a speed of 45 meters per second. That would be my final. The impact with the racket gives the ball a constant acceleration over a distance of 44 centimeters. I'm pretty sure with these being in meters, the speeds, we probably need that to be in meters. So we're going to say that that's 0.44 meters. We don't have time, so I need a formula with no time in it, no t.
Second. No.
This one? Okay. So b squared equals u squared plus 2as. 45 squared equals 0 squared plus 2 times the acceleration we're looking for times s, which is 0.44. This is 0.88a. What's 45 squared?
A large number.
What do you mean?
Anything.
2025.
And when we divide by 0.88, we get
2,301 meters per second.
2531. 2,531.25.
but we can't tell with that in your mouth.
Here we go.
Because it wasn't clear, I'm sorry.
2,531.
531. That's what he got. Is somebody check that?
That's not what I
So
got.
you said that? Oh,
Ah,
I divided
easier.
by 0.8, not 0.88.
Somebody else want to take a stab at it? 2301 was,
That's
yeah.
Yeah.
It was 2301, okay. And plug that in there, and you multiply by 0.058, and we get a net force of, was it 133?
Yeah, 133 newtons.
And based on significant figures, I guess we could say 130 newtons, if you were doing sig fig stuff. Because the 0.058, that's the number they gave you. 58, 45, 44, those all had 2, so your answer could probably have 2 sig figs. Not that I think that they would count it wrong if you put 133, just to be honest with you. Because they're kind of plus or minus 1 sig fig. Okay. During a circus performance, a 72-kilogram human cannonball is shot out of an 18-meter long cannon. If the human cannonball spends 0.95 seconds in the cannon, determine the average net force exerted on him in the barrel of the cannon. Okay, well, we've got his mass. We want to know the force. Guess I'm gonna have to sue that. Let's see, we need the A. They gave us 18-meter long cannon. He spends 0.95 seconds in that. Was he moving in the beginning?
No.
So we're going to assume he starts from rest. So we need something without a V. S equals UT plus 1/2 AT squared. So 18 equals 0 times 0.95 plus 1/2 the acceleration we're looking for times 0.95 squared. Okay, what's 1/2 of 0.95 squared?
0.45125.
0.45 what?
125.
Yeah, I'm not sure how significant that is, but okay. And then this will give us our acceleration. Since the numbers they gave us were all 2 sig figs, our answer should probably be 2 sig figs. So if you round it to 2 sig figs, what's the acceleration here?
39.889.
39.889. And times 72 gives you number of sig figs and all that good stuff. There we go. So we're okay with that? All right. So let's take it to the next level. Two forces, F1 and F2, act on a 5 kilogram block shown in the drawing. The magnitudes of the forces F1 is 45 and F2 is 25. What is the horizontal acceleration, the magnitude and direction of that block? So anytime you draw your forces, you always draw it from a point. So we have this one that's acting down, and in fact it would be acting down from the horizontal at an angle of 65 degrees, and this is F1, so it has 45 newtons of force that it's doing that. So we're just redrawing it from the center. And then F2 is completely horizontal this way. And I think they say that's 25 newtons, right?
Mm-hmm.
Now in this problem, they're only talking about the horizontal acceleration, so I need to sum my forces in the horizontal direction. Okay? So my net force is equal to mass times acceleration. I know I've got to be accelerating because the object is moving and they didn't tell me it was at a constant velocity. So I know that it has an acceleration. The mass of the box is 5. And I'm looking for the acceleration of this box. But I have to get the net force. I have to sum my forces horizontally. So here's kind of the way you do those problems. The first thing, anytime you see a problem with forces, you always draw out the forces that they give you. Draw the scenario they give you. Label all the forces that you have. Okay? Usually using the 5-force method. Then if there's any angles, you resolve those angles horizontally and vertically because it's going to break it down horizontally and vertically. You can only sum forces horizontal or vertical. You can't really do it when it's at an angle. Okay? So when we do this, we actually have to break this down into horizontal and vertical. How do you get the side? Sine. This would be 45 sine 65. That would give you a vertical. And the horizontal here would be 45 cosine of 65. And in fact, that's 19 newtons. Pretty sure that's 19 newtons. Somebody should check me. See if that really is. That is 19 newtons. So if I'm summing my forces horizontally, I don't really have to worry about that vertical, even though I could get it. I don't have to worry about it because it only wants the horizontal right now, right? So positive 19, because the 19 is going in a positive direction, plus, because it's summing forces, 25 in a negative direction. So 19 plus negative 25 is equal to the mass times the acceleration. So 19 minus 25 is negative 6 equals 5a. So a is going to be negative 1 point what?
2.
22?
Just 2.
Okay. Alright, so that tells me that it's going to move 1.2 meters per second squared in the direction of left. Right? Because it said magnitude and direction. That negative is indicating. Now, you never want to leave the sign on the front and then put a descriptor at the end. So if you say negative 1.2 meters per second squared, you can't put a descriptor at the end. You can say 1.2 meters per second squared to the left, or you could say negative 1.2 meters per second squared, but you can't put both because that changes it. If I have negative acceleration to the left, that's like slowing down in a negative direction. If I'm slowing down in a negative direction, that gives me positive. It's like in English, double negative, not really going to do that. Right? We don't do that. That's poor physics. Before we move on, I just want to make sure that if there's any questions that we address those questions. So, as to why or what we did or how or anything like that. I know for most of this is a review, but I know for my students it's been a while. It's been a while, but we've learned some vectors and math since then. Yes, that makes it better. It does make my life easier. Okay, we have a 12-kilogram lantern. It's suspended from the ceiling by 2 vertical wires. What is the tension in each wire? I wonder if it's a green lantern. So here's my picture. That's the first thing I always do. The second thing I do is label any forces. So do I have a weight?
Yes.
Yes, the weight would act down, right? Let's make these shorter. And then I don't have a normal force because it's not on a surface. The lantern itself is not on a surface. Friction, well, it's not moving, so pretty sure the lantern's not moving unless there's a hurricane. So we're going to assume that the lantern's not moving. So no friction. Tension?
Yes.
Yes.
Do it.
Now, one of the things I was concerned about and why I kind of made these a little bit shorter is because you want your forces to balance. The downward arrow should be equal to the sum of the ups. And so you can actually check that with a ruler when you're doing the IB exam, and it can help you to answer questions on forces. So if they're trying to see which one of these has the free body diagrams drawn correctly, one thing you actually want to do is check and make sure that the sum of all the horizontals equals 0. So however much I have going to the left, I have to have going to the right, and however much I have going up vertical, I also have to have going down vertical. You want those to actually sum up to be 0. You know, one of the ones that I've seen is we had a picture, and it was hanging from a peg. And they wanted to know the forces that were on the peg. Okay, first thing is, we're not talking about the picture, so we're not even dealing with the forces on the picture. So I just take the picture out of it to begin with. Now downward, I have what? Oh, I have 2 tensions acting down. Which means my up, to counteract that, has to be, because there's normal force, because the peg's going to act on it, right? It's a surface. It has to be 2 times as long acting up. Why twice as long? And that's probably a little longer than it should be, in fact, but why? Because there's 2 tensions, so this counts twice. Remember, the sum of the downs have to be equal to the sum of the ups when it's not moving or when it's in translational equilibrium, that's the case. So if it's at a constant velocity or not moving, the downs have to equal the ups. So when they're asking you questions about the free body diagrams, that's one of the things that you should be checking. Do the downs equal the ups? Do the lefts equal the rights? That generally will give away your answer. And they do a lot of multiple choice questions like that. Okay. Sorry, diverged a little bit, but that's why these are the way they are. Now in a lot of problems, you just draw the things on there. You're not worried about the length of the stuff, and that's because you're just doing a concept and you're trying to answer something. You're not trying to figure out, are these drawn correctly? But so you know, when they ask you to draw a free body diagram or draw the arrows on there, you need to be careful about that because you want them to be, okay? All right, so this is not moving. So when we say our net force is equal to mass times acceleration, it's not accelerating. So it's in translational equilibrium. Its net force is equal to 0. So let's sum these forces. 2t is positive plus the negative fg, right? And that's equal to 0. So 2t is going to be equal to fg when I move the weight of the object to the other side. Now I don't want to know what 2t is, I want to know what t is. But in order to get that, I'm going to end up having to divide by 2. So I'm going to take the weight and I'm going to divide it by 2. And this makes sense, and we actually use this an awful lot, and you probably don't even realize sometimes when you're hanging stuff up that you're using it, but you know that if you want to hang something, you're not going to hang it with one little tic-tac. Think it's going to hang up on the ticky-tack tape or whatever. You know it's not going to stay. Instead, you distribute the force among several pieces because that just makes sense. Well, this is why it makes sense. Because it's distributed equally among each piece. So, the weight, well, we have the mass of this is 12 kilograms, so can we get the weight of the object? How do you get the weight? Okay, so 12 times 9.81 is the weight, and that's equal to 2t. So t is going to be equal to 58.86. And, well, with 3 sig figs, I'm thinking this is probably like 58.9 would be sig fig wise appropriate. And that's because 12.0 has 3 significant digits in it. So what do you guys think about that? Huh? Yeah, we do have to be careful. There's a lot of little things with forces that can go wrong. And basically the thing that I would encourage you the most with in regard to a lot of that is when you are doing a problem in the multiple choice, you know that the force problems take a little bit longer. Okay? And so if I see a force problem that's not just like SUVAT, plug it in, net force equals mass times acceleration, I skip it and I go back to it. I would. Because it's going to take you a while to resolve those forces. And a lot of times some of the other, because they go in order by topic, the multiple choice does, so a lot of times if you're stuck on that one and you spend a long time, you have less than a minute. You have about a minute apiece on your multiple choice. Minute and a half, depending on, you know. So considering that, you don't want to spend a long time trying to resolve forces. When you want to make sure you at least get a chance to get to maybe some of the easier ones, like a half-life question that you know, by that time probably you're better prepared for and ready to go, you know. You might be able to answer the half-life question, or maybe it's something like alpha particle, or, you know, something maybe a little more something that you're more familiar with, that you feel more confident on. So if you spend a lot of time doing that one force problem, you're going to get stuck and you're not going to get through all the multiple choice, and then you're going to be like, well, I could have answered that. Yeah, you probably could have, but you ran out of time, so you didn't answer it. And that would have been an easier point than getting that force question. So I'm not saying skip it completely. Go through, do the rest of them, come back to it. Just make sure that you come back to it, you know? Now, obviously, you don't really have quite as much of an option when it comes to the written paper 2 stuff, when it comes to that. But in the multiple choice, I would definitely, some of them take a little longer, so unless you feel really confident in your force skills, skip it, come back to it. Don't get bogged down on a question. It's a bad idea to get stuck on a question, stay there for a really long time. That could be 3 or 4 other questions you could have gotten right in that amount of time. 4 points versus 1. And each multiple choice question only counts about half a point towards your overall IB physics score. So considering that, yeah, I've actually sat and done all that math. It's about a half a point towards your overall IB score. Which means it can make or break your IB score too. Because the other ones don't quite count as much. Some of them count like 0.36. Some of them are like 0.33, some of them are a little bit less than that, so keeping that in mind, your multiple choice is very important. Alright, let's look at this, this person. The diagram shows a traction device used with a foot injury. The weight of the 2.2 kilogram object creates tension in the rope that passes around the pulleys, therefore the forces of T1, T2 are applied to the pulley on the foot. It may seem surprising that the rope applies a force to either side of the foot pulley. A similar effect occurs when you place a finger inside a rubber band and push downward. You can feel each side of the rubber band pulling upward on the finger, and the foot pulley is kept in equilibrium. Net force is equal to 0, equilibrium. Because the foot also applies a force to it, the force arises in reaction to the pulling effect of the forces T1 and T2. Ignoring the weight of the foot, find the magnitude of F. Obviously, this is not as good as a symmetrical version of this picture as it should be, so my apologies. But you get the idea. And going from here, we have a weight acting downward. It's actually a mass that acts down. The mass is 2.2 kilograms. Bless you. Alright, you do have horizontal and verticals here. Okay? I want you to think about this for a minute. You do. Horizontally is on this plane. Vertically would be right here in this plane. Okay? This is just straight vertical. Remember, we're going to tilt our axes, so we can say this is our y-axis, and we're going to call this our x-axis. Okay? Does that help you guys? See a little bit? Careful. No, that doesn't really help you much, but my bad. Sorry. So what causes the tension T1 and T2? The weight. This acting down is going to cause the tension here, which is going to cause the tension there. So in fact, what do we know? T1 is equal to T2, which is equal to that. Look at the picture that you have and actually notice it's on a pulley system. So if 2.2 kilograms is applied downward, it's pulling the rope T2, right? Mm-hmm. So what we say is T1 equals T2, which is equal to the mass times the gravity of the object. So T1 equals T2, which equals the mass, 2.2, times the 9.81, and this is going to help us substantially. So T1 and T2 are equal to what?
21.58.
21.58. Okay. But they want us to find F, right? I want to find F. Find F. Now, if you weren't sure that T1 was equal to T2, let me tell you a way you could have known that. the vertical here is going to be the same as that vertical there.
Because they're both 35 degrees.
So this would have been T1 sine of 35, and this would have been T2 sine of 35. So if you weren't sure, and you felt absolutely confident about that, and you did not know, notice that these are the verticals, right? With our tilted axis, these are our verticals right there, right? So if I sum my verticals, and they're equal to 0 because we're in equilibrium, then I have T1 sine of 35 in the positive equal to T2 minus T2 sine of 35, right? Negative, which means T1 sine of 35 was equal to T2 sine of 35, and, well, that just frankly means T1 was equal to T2. And we know that the tension of that was created by applying that mass, as they told us in the problem. So if you did not for sure, without a shadow of a doubt, know that T1 was equal to T2, there was a way to figure that out. Okay, so before I move into the horizontal, I want to make sure everybody is with me and understands what we did. And this is an okay time to ask questions, so if you have a question, please ask. Don't sit there thinking that, you know, you can't speak up, because I want you to know this and understand. So everybody's okay with it? Yeah? Okay, well that's good. That's good news. That means we're on the right track. Now, because we had angles, we would have also resolved this horizontally as well, right? And we know it's in equilibrium horizontally. So we need to look at our horizontals. What do we have horizontally? Well, if this is T1 sine 35, what would this part be right here? T1 cosine of 35. And for this one over here, it would have been T2 cosine of 35, right? Because you have two triangles, so you would have had to get the horizontal for each one of those. So you had T1 cosine of 35 would be this side, and T2 cosine of 35 would be that side. Of course, we know T1 and T2 are equal, and we also have that value. So let's sum our forces horizontally. What do we have horizontally? We have negative F, right? And then we have positive T1 cosine 35, positive T2 cosine of 35, and that's equal to 0. We can move that to the other side, right? That would make it equal to F. T1 cosine 35 plus T2 cosine of 35. The great thing is, what do we know? We know that T1 and T2 are equal, but we also know the quantity, because it's equal to the weight of the mass that was hanging on there, which was mass times gravity, 21.58. So 21.58 cosine 35 plus 21.58 cosine of 35, or you could have just said 2 times that. Whatever works makes you happy. Which will give us the force that we were trying to get.
35.36 newtons.
Okay, 35 newtons, because they gave us the mass as 2 sig figs, so. But again, you have to break it down horizontally and vertically. And pretty much all of our force problems that have vectors in it, we break them down into horizontal and vertical, some at horizontal, some at vertical, and that usually will give us what we're looking for. Usually. If we did it correctly.
We're going to English review because we have a oral system.
Okay. Miss Woodruff and I knew about that and talked, so I know. Tell her I said hello. to appreciate you guys making it, even if it was just for part. Bye, thank you. Alright, I think we're in number 8, right? A 1.40 bottle of vintage wine is lying horizontally in a rack. That's about as good as my artistry gets. That right there. The two surfaces on which the bottle rests are 90 degrees apart, so this is in total of 90 degrees there. And the right surfaces make an angle of 45 degrees with respect to the ground. So this is 45 degrees here, 45 degrees there. We know this whole thing is 90, so with respect to a vertical, we know this is 45 and this would be 45. Each surface exerts a force on the bottle that is perpendicular to the surface. What is the magnitude of each of these forces? So perpendicular to the surface, it has a normal force. So they're saying a force is acted this way, and a force is acted this way. So rather than clouding up my thing, since this is this way, that's the same direction of that, right? And this is this way, which would be the same as, so to make life easier. We want to know what those forces are. We know they're equal. But there's one more force we haven't accounted for. Do we have a weight?
Yes.
Yeah. So we're going to have a weight. Trying to make them equal. 2 times this. That's why this twice as long. Trying to make them balance. Okay, so how are we going to do this? Well, horizontally, we've got angles, right? We know this isn't moving, so we know the sum of our forces is equal to 0. We've got angles, we need to break it down horizontal and vertically. So this would be sine, because it's opposite of the angle. So F sine 45, and this would be F sine of 45. Now, if I summed my horizontals and set it equal to 0, I have positive F sine 45, negative F sine 45. Imagine that they're equal. That's not going to get me anywhere. So let's look at the vertical. This is cosine, right? Because it's the adjacent side. Since that's opposite, this must be adjacent. So this would be F cosine 45. And this would also be F cosine 45. The great thing is that there is an additional force that's vertical, the weight of the object. And this mass was 1.40, and we know gravity's 9.81, so we could get the weight of the object, right? And it's what?
13.7.
Okay. So let's sum our forces vertically then. We actually, vertically upward, we have 2F cosine of 45. Now, since the angles are the same, we know that those are going to be the same numerically, which is why it's acceptable just to say 2F cosine 45. If the angles were not the same, then you'd have F1 and F2. So you have to watch for that. If they're the same angles, those would be the same forces. Not the same angles, not the same forces. Okay, and then downward we have FG, and that's equal to 0. So 2F cosine of 45 would be equal to the weight of the object, which is 13.7. So I think I can get F by taking 13.7 and dividing by 2 cosine of 45.
9.7.
Okay, 9.7 newtons. Okay, 9.71 with sig fixed. Thank you. questions about that? What'd you say?
And then I'm just laughing because when we learned forces, I thought they were so hard. And I was just like, not really.
And nobody trusts me. Serious, I've tried with the juniors to explain, and nobody trusts me until later, and then you go, okay, maybe I actually.
After they do the harder stuff.
Well, all the stuff that you did in that unit is harder than anything you've probably done since then. But everything in your math ability has gotten better since then, which makes this easier and makes everything else harder. Sounds kind of TOK-ish. It is. It's relative.
Everything.
Yes, and especially in physics.
I know.
Everything in physics is relative to something. Without a perspective, we don't know anything. Which is why physics and TOK really actually go really hand in hand. We really are teaching one giant TOK class in physics. We just approach it from a mathematical standpoint, which is a little more concrete, which makes us feel better about ourselves. Usually. I guess sometimes it doesn't make us feel better about ourselves.
Sounded like one.
But Nick, when I taught it to you, I knew that you guys did not have vectors, weren't as familiar with sine, cosine, and tangent because you hadn't done all that stuff in your class yet, and hadn't done graphs of motion. And I, every year, am faced with that same situation. And every year, when we get to this point and I start reviewing forces, I get the same responses. Why was that so hard? And I'm like, your math has grown. You guys have come a really long way. You've matured, your attitude has matured, and everything has changed. And so what once was a little bit harder becomes a little bit easier. And it's not your first time seeing it either. And you've got vectors covered in math, so you've seen it several times. So it gets better with time. All right, so the next one is steel I-beam has a weight of 8 kilonewtons. And it's being lifted at a constant velocity. That sounds important, doesn't it? That means our net force is equal to
0.
What is the tension in each cable attached to its end? We know these are 70 degrees from the picture. And this is the weight of the object. Let's make this a little bit longer. Is 8,000 newtons. Now, if I do this, I've got angles, right? So I gotta do the angles. We know the tensions are the same. This would be T cosine 70, right? And this would be T cosine of 70 on this side, which makes this T sine of 70, T sine of 70. Always pay attention to where they draw the angles, though, in the picture. Because if you're used to seeing the angles here, and all of a sudden they switch the angle and give you these angles there, it switches the problem. So pay careful attention to which angle they're giving you. Now horizontally, we know those are going to be the same because there's not another force. So if I sum my forces horizontally, I have positive T cosine 70 plus negative T cosine 70. That doesn't get me anywhere. So let's look at vertical. Vertically, I have 2T sine of 70 minus my weight is equal to 0. So 2T sine of 70 is equal to 8,000. So T would be 8,000 divided by 2 sine of 70. $4,260? Cool. Let's see. For time's sake, no, yeah, I think we can do it. No, we're fine. We're okay. This is supposed to go till 12:30. So that's a lot of them. We're not doing all those. Let's do the ones I see a lot. let's skip 11, go to 12. So I see this show up from time to time. You have a crane and a load. A crane is used to hoist a load of mass M1, 500 kilograms. The load is suspended by a cable from a hook of mass 50 kilograms, as shown in the diagram above. The load is lifted upward at a constant acceleration, so it's accelerating upward, and they tell us that's 2 meters per second squared. So we are accelerating our system. On the diagrams below, draw and label the forces acting on the hook and the forces acting on the load as they accelerate upward. So on the hook, we have a tension acting up, and they called that T2. We have a tension acting down because we have a load down, which is T1. And we also have the mass, right? The weight of the object for that one. On the load, you have a tension acting upward, which is T1, and you also have its weight acting down as well, right? Now, when you have two separate objects, you sum your forces on each object separately. So the sum of the forces on the hook equals mass times acceleration. We have T2 in the positive, T1 in the negative, Fg in the negative, and that's equal to its mass times its acceleration. Now, we don't know what T1 or T2 is, but I'm pretty sure we can get the weight of that object. The hook is 50 kilograms. And we know the acceleration is 2 because they gave it to us in the problem. So we know T2 minus T1, and we can actually find this value. Oh, we can use 10? That makes my life much better. So T2 minus T1 is equal to 600?
Yeah.
And I can't go any further than that. I need to do the next one, because I'm not going any further with that. I need to know something. So in that one, I sum my forces. It's equal to mass times acceleration. I have T1 minus Fg equals mass times acceleration. Now notice my accelerations are positive because I'm moving in a positive direction. So T1 minus the mass of this one is 500 times 10 equals 500, and the acceleration is 2, as given to us in the problem. So T1 minus 5,000 equals 1,000. So T1 is 6,000 newtons. Now that I know what T1 is, I can find what T2 is. All I have to do is take this and plug it back in. So T2 minus 6,000 is equal to 600. So T2 is 6,600 newtons. So when you have two objects, it almost always works that way, where you actually have to sum the forces on one, sum the forces on the other, and somehow they're going to plug in together. You're going to get one, and then you'll have to go back and get the other one. They almost always work that way when there's more than one object. Okay? The cable's lifting a construction worker in a crate. The weights of the worker in the crate are, here's our worker, here's our crate, two separate objects. The weights of the worker in the crate are 965 and 1510 newtons respectively. So the worker's weight is 965 newtons, and the load, or the crate, is, okay? The acceleration of the cable is 0.620 meters per second squared upward. What is the tension in the cable below the worker and above the worker? Well, we need to put those tensions on here. Right? So the worker has a tension above it. She also has a tension below it, which means this has a tension above it. Oh, you know what? That looks exactly like the problem we just did. Ironically speaking, yes, it is the exact same problem we just did. So let's do that. T2 minus T1 minus Fg equals, how are you going to get the mass of the worker? Okay, do that for us. The mass of the worker is its weight divided by 9.81.
98.30.
Times the acceleration, and there we go. Now, why did I do that? Yeah, that's the mass. We have the weight. We can plug in the weight. Hold on, we'll do that. T2 minus T1 and 965, 8.37, 620. So we can find T2 minus T1. So really, what we are doing is the exact same thing we had before. The only difference is they gave us the weight, which means we had to find the mass. And weight is equal to mass times gravity. So if you take the weight and divide it by gravity, you would find the mass that you needed for the form. Did you get us
1025.99.
I could have said 26. That would be nice. Okay, and then we do the other one, T1 minus Fg equals its mass times acceleration. So T1 minus 1510, what's its mass?
Yeah.
153.92. So T1 is Wow, I skipped number 10 and 11. I'm sorry. I meant to just skip 11. We'll go back and do it. My bad.
1,605.
Yeah.
You say what?
1,605.
Okay. And then we plug that back in to get T2. This T2 minus T1 was 1,025.99. So T2 is
2,631.
There we go.
Let's go back and do question 10 that I skipped somehow. Sorry. Don't ask me how I did that. A 43.8 kilogram sign is suspended by two wires as the drawing shows. Find the tension in wire 1 and wire 2. Yay. Notice we have two different angles. So whenever you have one, again, you identify your forces on it. You break your angles down horizontally and vertically. So when we break this down horizontally and vertically, since the angles are different, our tensions have to be different here. So sine would give us T1 sine of 43 on this side and T2 sine of 55 on this side. The sine is opposite, right? So opposite of the angle, we use sine. And then the adjacent side, this would be T1 cosine of 43. This would be T2 cosine of 55. Now that we recognize that our verticals are not the same and our horizontals are not the same, that means we have to sum them both horizontally and vertically. In this problem, they're not moving, it's stationary, which means our net force is equal to 0. We are in translational equilibrium. So let's sum our forces horizontally, and then we'll sum our forces vertically. Horizontally, I have T2 cosine 55 minus T1 cosine 43, and that's equal to 0. Now, I don't know if there's a reason to keep those angles around. Mathematically, it's just a number, right? So I'm just going to figure out what that number is. Cosine 55. 0.57 T2. 0.73 T1 equals 0. Now I can solve for one of these. Which one do you want to solve for? T1. Alright. So I'm going to move this to the other side. So T1 is going to be equal to